So, welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome David Wilner to give the talk this week. So, David received his PhD at UC Berkeley in 1993. He was actually working on massive star formation, a topic dear to my heart. We were doing some of the first millimeter interferometry on massive star formation. He then was a postdoctoral fellow at the Harvard Smithsonian Center for Astrophysics before becoming a NASA Hubble Fellow, also held there, and then joined the CFA staff, somewhat after that, where David has been since. David has done a number of roles there, including being the director of the radio division there, several divisions at CFA, but leading the radio group there, and instrumental in the development of the submillimeter array into the facility it is today. He's also currently the co-chair of the NGVLA Science Advisory Council. So chat with him about NGVLA as well, if you're interested. And today, of course, well, since his time as a Hubble Fellow, you've been looking at disks around young stars, and I think we'll hear about some of the latest work in that area today. So welcome, David.
Great, thanks for that nice introduction, Jonathan. It's really a pleasure to be here, my first visit to Sweden. All right, so the topic today is debris disks. What are debris disks? Debris disks represent the end state of circumstellar disk evolution. So we know that gravitational collapse with angular momentum forms disks, and these disks are integral to our paradigm for star formation, for planet formation. And the debris disks are a manifestation of what's left over after the star formation process, after the planet formation process. So disks around main sequence stars, what's left around main sequence stars. And they're interesting because by observing these disks, we can learn some things about planetary system architectures and about the evolution of planetary systems, particularly in the outer regions that are really hard to explore by other means. Okay, so in this talk, I'll go over a few things. I know many of you are new to debris disks, so I'll spend a little bit of time introducing debris disks in a little more detail and how we observe them, what we know about them. Then I'll focus on the particular role of observations at millimeter wavelengths and discuss some of what we've learned from ALMA about their structure, about their radial structure, about their vertical structure, and about asymmetries that may be related to the presence of planets. So that's the goal. And before I go on, I just want to hopefully, recognize a few people that I've worked with quite closely that contributed to all of this. Luca Matra was a postdoc at the CFA. Meredith Hughes was my student. Josh Lovell, who's currently a postdoc, and Meredith McGregor, one of my other students, have all contributed, as have many other people, to the work that I will discuss today. Okay. So what are debris disks and how do we observe them? So like a lot of, I'd say, very interesting phenomena in astronomy, debris disks were a serendipitous discovery. Back in the 1980s with the launch of the IRAS satellite. Some nearby stars were to be used for the calibration of these first far infrared observations of the cosmos. And one of them in particular was the star Vega, Alpha Lyra, which is the spectrum you see in the upper left. So this is just flux versus wavelength, and the four wavelengths that are listed there, 12, 25, 60, and 100 microns, were the bands of the IRAS satellite, and that solid line is the expectation for the stellar photosphere. It's just the Rayleigh-Jeans part of the stellar photosphere. But when the observations were made, in fact, the points out at 12 and at 25, 60, and 100 microns were way above the stellar photosphere. So it didn't take long to realize what was going on here, and this was seen around a number of nearby stars, that there's dust emission in the circumstellar environment that's heated by the starlight and reprocessed. So it doesn't take very much dust. It's a tiny amount. And in these cases, it's less than 0.1% of the stellar luminosity is being intercepted by dust in the circumstellar environment.
How much dust is there? Or are you going to say?
No, it's like an asteroid's mass worth, roughly. So yeah, not very much. But it shouldn't be there, okay? Because the radiation pressure on the dust from the star, especially an A star like Vega, should push the dust out on very short timescales, 10,000 years, something like that. The stars are, 400 million years old. So what does that mean? That means that the dust has to be replenished. And so the theoretical idea that this led to was that there are reservoirs of kilometer-sized bodies that are colliding and continually producing dust, which is why we see this far-infrared excess over the photosphere. Okay, so why disks? Okay, so a star like Vega has, first of all, essentially no dust extinction. So it's not that the dust is arranged in like a shell around the star, because you don't see any dust against the star. But how is it distributed? So there was one system, Beta Pic, which is the one in the lower left here, which was quite quickly observed with a coronagraph and shown to, wow, have this beautiful scattered light nebula in an edge-on disk morphology. So we have dust, which comes from debris from kilometer-sized bodies, presumably like asteroids and comets in our solar system that are left over from the formation of planets, the building blocks of planets, and they're arranged in disks. So just a comment, as I said, these are the descendants of protoplanetary disks. They're the end state. But they're really quite different in their physical properties, in the sense that many of you I know in this room work on star and planet formation. Those circumstellar disks are gas rich, right? It's gas and dust from the ISM. And you imagine that the dust in those disks is colliding and sticking and building up and turning into planets, right? In these debris disks, the gas is gone. You have these building blocks of planets that are colliding with each other, grinding down and producing new dust. So they're very, very different physical pictures. And these disks are very tenuous. Just a tiny amount of dust is there, but we can see it because it has a lot of surface area. So that's great. Okay, what do we know about the demographics of debris disks? So the basic model is that essentially all stars have a planetesimal belt, like our asteroid belt or the Kuiper belt, that has some radius and some amount of mass in it, and it's ground down by collisions. So when we observe nearby stars, particularly in the far infrared, we get this kind of plot. So on the y-axis is the fractional luminosity of the dust. So you see these numbers, 10 to the minus 4, 10 to the minus 6, right? So it's less than 0.1% is what you can see. And this is effectively the same as the optical depth of the dust, if you want to think of it that way, very, very low. And on the x-axis is the temperature of the dust, which you can think of as a radius, if you want. If there's radiated equilibrium heating the dust, then you just get a radius. So the upper curve here is the sensitivity curve from Spitzer at 70 microns, and the lower curve is from Herschel at 100 microns. And this plot comes from an unbiased survey of essentially all the nearby FG and K stars, so sun-like stars, and about 36 out of 177 are detected, so about 20%. And the sensitivity here is down to a fractional luminosity of something like 10 to the minus 6. And the expectation is that if we had more sensitivity, one would see fainter and fainter belts. So we can only see the dustiest ones, the top 20%, but there are probably more.
And the sun would be...
yeah, I'll get to that in just a second. So then there are about 400 debris disk zones from their far infrared photospheric excess in the far infrared. And yeah, you might wonder, right? So these curves are for stars at 20 parsecs. You might wonder, if you were at 20 parsecs and look back at the sun, could you detect a Kuiper belt, for example, just the biggest one? And the answer is not quite. So the Kuiper belt out at 40 AU has an effective temperature of something like 50 K from heating by the sun. But the fractional luminosity, as estimated in various ways, is sort of a few times 10 to the minus 7. So we can detect dusty debris disks around other stars, but the astronomers on other stars can't see the one around the sun, unfortunately. Okay. So here's the bit of physics that makes this fun, is size-dependent dust dynamics. So as I mentioned, the idea is you have these large bodies, they collide, they make smaller fragments. The smaller fragments collide, they make smaller fragments. Those collide, they make even smaller fragments. Eventually you get down to micron-sized dust. If you make small enough dust, then it suddenly starts to feel radiation pressure from the star and perhaps stellar winds, which is a size-dependent force. And like gravity, which is a 1 over r squared force, radiation pressure is also a 1 over r squared force. So if you're a fragment of something and you get ground down to something smaller, and now you're a smaller fragment, suddenly it's like you have less gravity and you're just into an unbound orbit, right? So that's parameterized in various ways in the debris disk literature. But the bottom line is micron-sized grains get blown out, and millimeter-sized grains, well, they're pretty impervious to the radiation pressure and winds, but they don't actually even get that far before they collide and get smaller. So the cool thing about the millimeter-sized grains is that they more or less trace the dynamics of the parent kilometer-sized bodies. So that's the basic idea. So you should have, in your mind pictures of like Kuiper belt objects, like Arrokoth here that New Horizons visited, and they're colliding and making smaller and smaller things. Okay, so since we can't observe the kilometer-sized bodies, they're way too small.
Sorry, could it just be comets? I mean, comet stuff that comes in, why does it have to collide? Or are you going to come to comets?
It is comets. They are exocomets, right, in a sense. But why do you need to continually replace the dust? And as you will see, when you image it, it's out at 40 AU and not being evaporated near the star. So yeah, so you need a reservoir of them, but they are comets effectively. Right. So so the millimeter-sized grains trace the planetesimal orbits. So now we need to observe the millimeter-sized grains. And the way we can do that is observing at millimeter wavelengths, right? So this is actually a good discussion topic if you want to ask me afterwards. Why is it that millimeter wave observations trace millimeter-sized grains? That's a more subtle answer than maybe it seems, but let's just go with that on faith for the moment. So it turns out that for many years, actually, the only imaging observations of debris disks were images of beta Pic, because beta Pic's close by, it's 20 parsecs away, it's edge on, so it has a high surface brightness and you can observe it fairly readily. And so by the late 1990s, early 2000s, all of this sort of basic physics that I just described had been worked out in some detail. And so the model for beta Pic has the following kind of characteristics. So this is a plot from Bogerow et al. 2001 of the relative surface density of particles of different sizes versus radius from the star. And so the hypothesis is that there's a belt of large bodies, of planetesimals, out around 100 AU in this case. And then the millimeter-sized dust, which is generated by collisions in the belt, sort of sticks to the belt. And the micron-sized dust gets blown out into this big halo. So there's a prediction, in fact, that the millimeter emission should be confined to a belt. And all one needs is a telescope with enough angular resolution to observe that and check and see if that's okay. And so we were finally able to do that with the SMA in the mid-2000s. For the observers in the audience, Beta Pictoris is at a deck of -51, so it's quite far south. And it can be observed from Mauna Kea, but it doesn't get very high in the sky. Mauna Kea is at 19 degrees latitude. So beta Pic kind of does this on the horizon, doesn't even get to 20 degrees. But we were able to observe it. So this is the image, and those sort of lane contours there are the millimeter emission, which you can imagine the two peaks is essentially an edge-on belt, which is limb brightened in some way. And then the background is scattered light from micron-sized particles, as seen with HSD. And it turns out it's in the right place as expected from the models. And that was great. This is really a confirmation that the basic picture of this so-called birth ring of the dust was correct. Certainly one of those highlights where you have a prediction, you make an observation, and wow, it actually works. That was pretty cool. Okay, so then we have ALMA. Then we have a much more powerful millimeter wave telescope in Chile, and we can observe many more of these. And over the last decade, sort of piecemeal observe various debris disks. So these are some of the more spectacular ones as observed by HST in scattered light from small dust particles. And when you look with ALMA, you see a belt, and you see a belt, and you see a belt. See a belt, that one's a little more interesting, and you see a belt. And that's, they all have planetesimal belts. So that's pretty cool. Okay. So when Luca Matra came to the CFA as a postdoc, we discussed the fact that, well, now there have been a lot of debris disks observed with ALMA in a lot of different programs, in a lot of different ways, and not very completely. So we decided we should put all this together into a population study. What do we really know about particularly the radii of the belts and where they are? So we did some new observations with the SMA of ones in the north that ALMA can't see, and about 15 of them that ALMA had missed for various reasons that were bright enough. And this is called the Resolved ALMA and SMA Observations of Nearby Stars reasons. A lot of them actually were previously observed with the single dish JCMT telescope to get a millimeter flux, which helped us get ALMA time. That was called the Scuba 2 Observations of Nearby Stars, SONS. So this was RESONS. There's a play on words there. Anyway, these observations are not particularly high resolution, but they're enough to just resolve the belt structure. So sort of tens of AU. Essentially all of these are within 100 parsecs. Some of the youngest ones are a little further away. But we could do a uniform analysis and have a legacy data set for the community on millimeter observations of debris disks. So this paper came out earlier this year, and all the data is available, and it's very easily accessible. So if you're interested in this, it's a fun thing to play with. And here's the gallery of all of the debris disks observed by ALMA and the SMA. So all 74 of them. We all have our favorites for one reason or another. Beta Pic is in here, Fomalhaut. I don't know. A lot of them just have HD numbers, but they're dear to my heart. HD 1811327, whatever. But they're really spectacular. And what you see is essentially right there. They're all rings seen in different geometries. And from these data, we can extract a radius and a width and an inclination, and in some cases, even a vertical scale height, such as it is. So we did this uniform analysis of all of this data. So this is model fitting in the visibility plane with a very simple structure. So it's essentially just Gaussian. It's just a Gaussian centered on a radius with a Gaussian width, if it could be measured. And you can see these are some examples: data, model, residuals, and the fit in the visibility plane to the azimuthally deprojected visibility curve, for those of you who like Fourier transforms. But you can see, I mean, the data quality varies, but for the most part, you can do a pretty good job fitting a belt because it's just a Bessel function in its Fourier transform. And so you really just need to know where the null is. And the data is really quite good enough to do that. Okay, so now we have this collection of radii and widths. What can we do with that? All right, so now we can finally look at these as a population. So here, this plot, ignore the lines on it for the moment. So this plot is the mass of dust that we see versus the radius of the belt that we find. And we've grouped the sample into 3 age bins. So it's actually pretty difficult to age date stars, individual stars. We're not terrible at it, but we're not that good at it, particularly once stars get to be a giga-year old. Is it a giga-year? Is it 2 giga-years? Well, for the purposes of this plot, it doesn't matter. So we have young ones, sort of less than 30 million years old, and those we can identify pretty well because they're in moving groups where we can date low mass stars and whatnot. Then there are intermediate age ones and older ones. And what you can see, I hope, from squint, right, is that the belt masses deplete over time. And this is one of the main predictions of these collisional evolution models. And indeed, that is what we see. And also smaller belts deplete faster. And this is something that is also a key prediction of these models, because when you have a smaller belt, you have faster orbital velocities and you have more collisions per unit time, and you deplete the mass faster if you're closer in. And this was all predicted based on essentially photometric observations from Spitzer of A stars. And Mark Wyatt created a model. And these curves are basically from Mark Wyatt's model, and they do a pretty good job matching the data. So it's quite a simple view, but it does a good job describing the data. All right, the next key result is the following. We not only measure the location of the belt, but the width. We don't have great resolution in all cases, but we measure widths. So this was actually a little bit of a surprise. The classical Kuiper belt is actually quite narrow, and that's at the green line here on the plot. So this is fractional width versus number of systems, so it's a histogram. But many of them actually are quite broad in the sense that their fractional width is sort of unity. If you compare that with protoplanetary disks, which have been resolved into, many of them are resolved into rings. Probably many of you have seen these ALMA images of protoplanetary disks with rings. Many of them are actually quite narrow. And so this distribution is somewhat different and does lead to the question whether the structure is inherited from the protoplanetary stage, doesn't look like it, or whether it's evolved in some way. So one question you can ask is, are these belts really wide? Or do we just not have enough resolution to see that, in fact, they are made up of individual rings? So I don't have the answer to that. Well, I do have the answer to that, but I have a partial answer, but we'll get to that at the end. Okay. But then we have a handful that we've really hammered on with ALMA and observed in great detail. And this is one of my favorites. So this is Fomalhaut. So this is an A star, which is only 7 3/4 parsecs away. It's Alpha Pisces. You can see it with your eye, right? It's a first magnitude star. And here's our ALMA image. This was in Meredith McGregor's thesis at 10 AU resolution, which is pretty cool. So the first thing that you'll notice about this image is that the star, which you actually see the photosphere of the star at millimeter wavelengths, is not in the center. And the reason for that is, well, the ring is eccentric. So this was actually already known from HST observations in scattered light, but this is pretty impressive demonstration. I love it. It's such a narrow ring. It's such a beautiful map. And this was also inferred actually from Herschel observations, which resolved this quite well. So here's the Herschel map. And the thing about the Herschel map is, while it's brighter on one side than the other, it's brighter on the side near the star, and that's because it's warmer there, because it's closer to the star, so it's a little bit brighter. So this is a phenomenon that was called a pericenter glow by Mark Wyatt back in the day. And it's a beautiful illustration. If you look at the ALMA image carefully, you can see that the apocenter, the other side, is actually a little bit brighter than the pericenter. So why is that? That's basically because in Keplerian orbits, things move slower up there. So you have more material up there. And the millimeter is giving you kind of a product of temperature and mass, whereas in the Herschel observations are basically showing you temperature. So that's kind of a neat little result.
Is that ring resolved then in the millimeter?
Yeah, great question, Jonathan. So marginally at this resolution, but here it is resolved. Okay. So in fact, that sort of simple Keplerian model makes a prediction for how wide the apocenter should be relative to the pericenter. And it turns out that that the sort of 0th order model doesn't work because the apocenter is too narrow and a little bit bright, and the pericenter is a little bit too broad. So it turns out to fit these data, you need an eccentricity gradient across the ring, believe it or not. So this is dynamics. And so Josh Lovell actually is the one who worked this out. This paper is nearly accepted. And you need an eccentricity gradient that actually falls with radius. And it turns out that one relatively easy way to do that is to have a planet interior to the ring, and that modifies the eccentricities with radius. So there's probably a planet driving this, which we might have guessed from the eccentricity, but we have yet to see it. So this is a pretty subtle effect. You can really only see it at this very high resolution, but it's pretty neat. Okay. I'll just mention JWST is revolutionizing this field in its own way. And this image of Fomalhaut is quite incredible. So you notice that there's really bright mid-infrared 25 micron emission inside the ring. And moreover, it's actually structured. It turns out that this is pretty well explained by the phenomenon of Poynting-Robertson drag. So grains of modest size actually spiral in to the star. But as they're spiraling in, they actually collide and make smaller grains. And Mark Wyatt had a student who made this model actually some years ago and then was applied to Fomalhaut just this year. But if you look at that JWST image, you can see there's some additional structure. It's not just a smooth set of emission with radius, and that probably requires another massive body to structure it.
So there should be millimeter emission from the inner region as well.
Yeah, so not very much, as it turns out, because very little mass actually gets through, and you get most, the small grains are very efficient mid-infrared emitters. And so the ALMA data gives you a limit, right?
Have a limit there.
And it's all consistent. So there's actually almost no mass. That gives rise to this very bright mid-infrared emission. All the mass is in the belt. What time do I need to stop, Jonathan? Just so I know.
Another 5 minutes or so,
Okay.
5-10 minutes even.
All right, so let me say a word about vertical structure. So if you have a planet, it'll stir up the planetesimals and effectively increase their inclination dispersion. And so one can hope to measure that. And the poster child for this one is AUMIC, which is an M star at 10 parsecs. And the one way to think about this is the dust velocity dispersion is sort of excited to the escape velocity of the largest bodies. So you can, by measuring the thickness, you can get a constraint on what are the largest bodies in the disk. And that turns out to be at least 400 kilometers in AUMIC. but it can't be too big because then you blow up the scale height. So the maximum amount of mass in these bodies is only a couple Earth masses. So no Neptunes in AUMIC. It's actually quite flat. And the reasons results show that this is reasonably typical, although some have higher scale heights than others. Beta Pic is kind of a special case because its vertical profile looks like it has two components. So there's a kind of narrow component, but then there's sort of a broad component superimposed on that. And that suggests perhaps that there are two dynamical populations. So there's like one population that's very flat, like our Kuiper belt, like the classical Kuiper belt. But then there's another population of bodies that are colliding that are actually quite excited to higher inclinations. So that's exactly what we see in our solar system, right? So this is the distribution of inclinations of Kuiper belt objects going back, and this is when Kuiper belt objects were first detected. And there are clearly two populations. And the thought is that these excited ones actually come from the outward migration of Neptune at an early epoch in the solar system and knocked all kinds of Kuiper belt objects in higher orbits. And so Beta Pic looks very similar. It's interesting. I'm going to skip gas. So the last couple minutes, I'll just introduce this ALMA Large Program, which is called ARKS. So what ARKS aims to do is to make detailed observations of a larger sample of some of these debris disks, and it sort of uses reasons as an inspiration. Now we know which ones to pick, which ones we can observe. And we're after the radial substructure. Are these wide belts common? Are they really wide? Or are they narrow belts that just look wide because we don't have enough resolution? Same thing with the vertical substructure. Are these two component disks common or not? Maybe that has something to tell us about what Neptunes do and what kind of planetary masses might be in it. And if you want to talk about gas, we can do that later. But some of these debris disks actually do have some significant gas, and that's interesting. So this is a huge team. It's 50 people. And it's pretty wild. So just at the end here, I'll just show you what these data look like, because it's pretty cool. So this is the reasons data. So 6 of these objects are archival that have been observed actually really quite well with ALMA, like AUMIC there on the third on the bottom row. But a lot of them are blobs. So I don't know, like if you look at HD 32297 in the upper right corner, and we go to the ARKS data, you can see it's a lot better. So now we have a small sample, at least, of debris disks that observe very well, and we're in the process of working out all these questions. And the first set of ARKS papers actually should be submitted this summer, so you should see them pretty soon. And that's the end. Here's the summary. So what are the things I want you to remember? I want you to remember that millimeter emission in debris disks traces the large dust that traces the dynamics of the planetesimals. As far as radial structure goes, many of the belts are wide. There are gaps in some of them, but we really need more observations. The vertical structure, well, can probe for the presence of migrating Neptunes. And ARKS is coming, so stay tuned.
Great, thank you very much. Okay, so questions, please raise your hand online or here. And I was going to ask about the gas, but we'll take Leon's question first.
I'm wondering, back on the first slide, if there are going to be any instruments coming up that can detect things like the Kuiper belt at micron wavelengths.
Yeah, right. So that's a great question. Let's see if I can go back to this.
I mean, as faint as the Kuiper belt at micron, 100 micron, is it very?
Yeah, I forget the scale.
Okay.
There's something like that.
So, so this is a 2-part answer. You might think all you need is a little more sensitivity, right? And you could detect the Kuiper belt, right, based on this plot, right? It's not that much more sensitivity that you need. And there are missions that are proposed that could do that. So in particular, right now, one of the NASA probe class missions called Prima, which you've heard of, is in contention for going forward. That would have more than enough sensitivity to do this. But here's the problem. Prima is a small telescope. It's 1.8 meters or something. So the angular resolution is, well, it's actually roughly the same as the Kuiper belt out at, say, 10 or 15 parsecs. But the sky is not empty at far infrared wavelengths at these very faint sensitivities. So there are, unfortunately, all these dusty galaxies that fill the sky. And in fact, on average, there'll be at least one, if not more, in your Prima beam when you look at a nearby star. So the confusion from the background is actually a limiting factor at these levels. Now, there are ways to mitigate that. If you're close enough, you actually can potentially resolve the belt at least a little bit with a telescope like Prima. Also, galaxies tend to have emission lines and various things, so you could follow up and see, are there paws or something from the galaxy? So it's something that we're kind of on the verge of with the next generation far infrared space observatory, but it's actually going to be a little bit harder than it has been.
So the confusion limit is right just below here then from the...
Yeah, the confusion limit is kind of right there. In fact, Herschel basically was right at the confusion. And so going deeper is harder, unfortunately. But for nearby stars, it's not out of the question. It just will require a little bit of finesse.
And the closest stars then, are we already sensitive down in Alpha Centauri or places like that?
Yeah, the very closest ones, we're kind of at that level, at Kuiper belt level, the very closest ones, 1 parsec, 3 parsecs.
So has something been seen in Alpha Centauri?
No. Of course, its binary nature probably affects that. It may not, a belt at tens of AU is probably not stable long enough and that kind of thing.
I see Nick Bowering. You have a question?
We have a debris disk expert in the audience.
Hi, can you hear me okay?
Yes.
Okay, so there's a handful of these debris disk systems that actually have directly imaged giant planets like Beta Pic or HR 8799. And in my mind, at least, it seems like these systems tend to have the wider planetesimal belts, whereas like Fomalhaut or HR 4796, these narrower belts, we don't see the planets directly. Maybe the planets are too low of mass to directly image. So I didn't know if that sort of trend is holding up in the sample once you have better resolved belts, and if there's a good explanation for correlation between giant planets and wider belts.
Yeah, so you might imagine that there could be a correlation because migrating giant planets would do a lot of scattering of the planetesimals. So even if they were born in a narrow ring, you could make it broad with a scattered halo. And there's a model for HR 8799 that is reasonably consistent with that. The issue is, you're right, there is kind of a trend that particularly the A stars with directly imaged giant planets tend to have pretty massive debris disks. They also tend to be young, like 20 or 40 million years old, like Beta Pic or HR 8799. But the sample is so small that I'd say it's somewhat dangerous to extrapolate still. So if we find more giant planets, directly imaged giant planets out at tens of AU, we'll have to see. Now, of course, people are turning this argument around with JWST, and you say, well, we know of systems that have these massive debris disks. Maybe those are ones that have giant planets that we can detect with JWST. And so, as far as I know, that hasn't paid off yet, but there may be data that does. A good counterexample is Vega. Vega has quite a broad and face-on debris disk, which is quite massive. And JWST doesn't see any planets yet.
Yeah, that's right. All right, thanks, David. Great talk, by the way.
Well, thank you.
What is the most massive or earliest type star where you have a debris disk then? Do you have around B stars or
It's a really good question. Yeah, I don't know. I don't think anything very systematic has been done around B stars.
Well, what's the earliest type you have?
I mean, I'm just thinking, like Vega is an A0 star, right? So sort of earliest A star is a very prominent example. The detection frequency around A stars is a bit higher than for sun-like stars because they're easier to detect, they're more luminous. My guess is there probably are late B stars where there are debris disk detections, but I don't have them in my head.
Well, maybe we can think about that a little bit.
You touched on this earlier, but how do millimeter wavelengths detect dust? Because as far as I know, radio waves are not obstructed by gas or dust.
Oh, yeah, okay. All right. So I have a slide that is based on one from Meredith Hughes that's probably worth pulling up for this, because this is sort of a interesting pedagogical discussion. I guess I'm not sharing anymore. Let me see if I can find this slide. Come on. I know I have it. Yeah, okay. I need to find my Zoom window so I can share again. Okay. All right, so that's sort of a general statement that when you look at scattering or emission, the grain size is roughly comparable to the observing wavelength. Okay, so there are two parts to this argument. So the first thing is, when you think about grains, how do they emit? So this is a plot of the emission wavelength versus the emission sort of efficiency. So this is optics, grain optics. So if you're a grain, in this case a spherical grain, and you want to emit at short wavelengths, you're pretty efficient. It's easy, right? But when the wavelength starts getting to be the size of the grain or bigger than the grain, it gets harder and harder for the grain to emit efficiently. Okay, you have a bigger grain, then it emits more efficiently at longer wavelengths, and an even bigger grain at longer wavelengths still. And there's a turnover in the geometric optics, limit at 2 pi times the grain radius. Okay, so that's one part of the argument. The other part of the argument is that, here's the summary. I think these are Meredith's words. At a given wavelength, large grains are the most efficient emitters. Okay, now we have to worry about the fact that we have grains of different sizes. So this is a plot of the number of grains versus their size. So in debris disks, the sort of canonical size distribution is this size to the minus 3.5. It's a very steep power law. This is what you generically get when you crush things. Like if you take a bag of cookies and you smash them on the table, that's the grain size distribution.
This is also the size of the diffuse size then, isn't it?
Yeah, that's right. It's basically very generic result. I mean,
but one might expect it's different in debris disks than in diffuse size M, but it's not.
It's not, because you just get this whenever you have a self-similar fragmentation. So at some point when you're too small or too big, it's not self-similar anymore, either because of the material strength or gravity or something. But for a wide range, you get this. Okay, that was a distraction. But the bottom line is you have a lot of small grains and not as many big grains, right? So there are many more small grains than large grains in this kind of distribution. And so the small grains dominate the area. So the large grains are the most efficient emitters, but the small grains dominate the area. So you have these two things kind of competing with each other. But the net effect is that the smallest grains that can emit efficiently dominate, And so those tend to be essentially right at the near the turnover. So that's my pedagogical explanation of this. But you do need both of these things to be true. So if you have some pathological grain size distribution, or you have, grains that are needles, or, something, then, it can be different.
But is there any evidence the dust is different in debris disks than, compositionally or grain size? You said the size distribution is.
Yeah,
Sure.
so, people look at like silicate features in the mid-infrared and stuff like that. And I mean, to first order, no, right? I mean, in terms of composition, it all kind of looks like ISM materials, which is where it started, after all. So there are occasionally pathological situations, usually having to do with quite warm dust, where you might invoke some massive collision that resulted in melting or vaporizing the grains or something.
And polarization information, does that help, or is that all due to scattering, or is there anything else?
Yeah, so there's not a lot of information on that from the millimeter side. There have been polarization observations of the millimeter grains in beta pic with ALMA. If I remember correctly, you get more of a handle on the largest sizes than anything else, but I don't think there were any big surprises there.
Well, I did want to ask about the gas, because this is how I often hear about, they found gas, and how can there be gas? So,
right.
The actual transition from protoplanetary disks to debris disks, and what's the boundary? Is that all?
Okay, so those are two different questions.
Yeah.
I'll say a word about gas, because the gas is actually quite amazing to me. So I would say, for many years, people would say, well, debris disks don't really have gas. But that's not true, or it's sort of obviously not true, because the planetesimals that are creating the dust should be icy, right? So when they collide, there should be a way to release release gas. So many debris disks actually with ALMA now do have detections, particularly of carbon monoxide. So carbon monoxide is like super volatile, right? It comes off the grains at 20K. And so the poster child for this is beta pic, which has some weird asymmetric distribution of CO. But when you actually look at the velocity field, it's a Keplerian velocity field. It's just super orbiting. And it's essentially coincident with the dust belt. So that's good. Most debris disks, you can't see it like you can in beta pic. But if you're clever, you can do some stacking, and you can dig it out. So Fomalhaut, remember, Fomalhaut was this beautiful ring, right? If you just look at the ALMA CO data cubes, you see nothing, okay? But if you say, well, suppose I know that the CO is coincident with the dust belt, and I know it's in Keplerian rotation, and I know the mass of the star, right? Then I can stack it all. And indeed, when you do that, you actually pull out a signal. In fact, you pull out the signal on the top just by averaging it all. Then there's an ambiguity. Which direction is the disk rotating? So if you put in the right direction, you get a bigger signal. And if you put in the wrong direction, you get nothing. And actually, that's what convinced me that we were actually detecting it. When I saw the green spectrum, I was like, well, it is at the stellar velocity. Kind of looks like it's probably real. But with the Keplerian addition.
That's the red one.
Yeah, the red one, you actually pull it out. And that's sort of as good as it gets, typically. There's a subset of A stars that are actually very CO rich. And those are confusing. They've been known actually since the 90s. Ben Zuckerman discovered these things. But and there's a bigger and bigger population as people have looked more and more. they're still relatively rare. They have an outsized amount of attention from observers because they're quite bright. I mean, they look like protoplanetary disks in CO. And so the question is, well, what's going on with those guys? Are they somehow especially long-lived disks that really aren't debris disks, or the dust looks like debris, but I don't know. It's actually been a very confusing situation. But there's a model that I think makes a lot of sense and probably explains most of them, which is that if you have enough CO input into the gas, okay, and then it's especially around A stars, the CO is photodissociated, and you make some neutral carbon and oxygen and eventually ionized carbon. It turns out that by coincidence, the neutral carbon can shield the CO from photodissociation in the UV. So Kenton Krall, who was a student of Mark Wyatt's working on debris disks, figured this out. And there's a whole series of papers, and you can show that if you can produce the CO fast enough, the CO can effectively be shielded by the carbon. And so you can build up a whole lot of mass of CO.
It's not self-shielding of the CO, it's shielded by the atomic carbon.
Yeah, isn't that wild?
But isn't that in standard PDR models then that they need to account for that, or?
It is, I think. But usually you have molecular hydrogen around, right? So in this case, you don't have the molecular hydrogen.
Okay,
right? So that's the big difference.
Right. Right.
So that creates a whole different and interesting chemical situation, but it also creates an opportunity, actually, because when in all of these instances, you can imagine you're actually getting at the composition of the planetesimals, right? And that's something in the solar system. We wait for comets to come in and boil off, and we observe them like crazy while they go whizzing by the sun. But you can imagine in these disks of extrasolar comets, right? You could potentially probe their composition.
Did you have isotopes?
Yeah. So in these bright ones, the CO-rich ones, you can detect 13CO, and I think even C18O. But people have looked for other species like HCN, and so far nothing.
So it's just CO detections.
So it's just CO and the carbon, and there are also Herschel observations of atomic oxygen as well. Yeah.
Okay.
So
yeah.
So I have another slide which is relevant to this, which is just to say that in every ALMA observation of a debris disk where you'd expect to detect gas because you're deep enough based on your estimate of the mass loss in solids from the dust, you detect it. So that story holds together, right? These are icy comets.
We have a comment. Kay, did you want to verbalize your comment to us?
Yeah, please.
Well, I think it's better that Renee says it, but I think they have discovered sodium gas in beta peak disk that has been shown to be rotating Keplerian in a Keplerian orbit.
Yes, so beta peak is special in a number of ways. It's just bright and close, but indeed there are optical lines that emission lines that have been seen in many atomic species, and also one can do UV absorption spectroscopy towards the star, and so there are also lots of interesting things one can see in that, and that's actually something that Luca Matra and I have been pursuing in some other edge-on debris disks. The UV spectroscopy is incredibly sensitive and powerful for detecting even CO and carbon.
So let me see. So the gas is understood, but you're not seeing other species. So water would be hard to see, I guess.
Right. You'd like to see water. So this is potentially something you could think about doing with JWST in absorption. Potentially.
Right. Well, we're near the hour, but what about this transition from protoplanetary to debris? Is there anything to say about that, or it's...
Yeah, so I I don't have a lot to say about that, except to say that it's a little bit murky, right? Because in a protoplanetary disk, your dust is evolving, it's colliding and fragmenting also. It's just, to me, the sort of physical difference is that in the protoplanetary scenario, it's really hydrodynamics that are dominating. Whereas in the debris disk scenario, where you're very gas poor, you're really in a classical dynamics regime. Now, obviously, there's a crossover that has to happen. But my impression, at least, is that happens very quickly. So, at roughly 10 million years, you pretty much only see debris disks. That is, the fractional luminosity in the dust is very low. Whereas at a few million years, it's very high. You have these optically thick gas-rich disks. And so somewhere in between, right, things change relatively fast. But it's a great question and certainly an area of quite active research. The challenge is we don't have a lot of stars nearby that are 10 million years old or 20.
Mm-hmm. So when you're doing infrared access, I mean, we often use infrared access to find young disks,
right?
But a star that's 30 million years old,
yeah, and has a 1% excess. Right.
That's what is that? Is that a debris disk or is it a remnant to protoplanetary disk, or is it, it's the
right?
same?
So it's hard to tell, right? In some sense, and it maybe is a semantic question,
right?
At some level.
But does everything have an infrared excess at the level of 1% at 30 million years, or I guess?
Well, we don't know, right? That's I mean, in some sense, that's the question, right?
Yeah.
Because particularly if it's out at Kuiper belt distance, it's too cold to know from the near infrared or the mid infrared.
Yeah, thinking more of the James Webb MIRI. If we're using MIRI to find young disks, that may be
right. But even 20 microns, you need pretty warm dust.
Mm-hmm.
You need asteroid belt kind of dust.
Yeah,
Kuiper belt dust. Yeah.
Last question, quick question.
Yeah, I've seen the white circle in many of the plots. Just didn't quite catch what this is. Is it show how opaque?
Yeah, the little white circle in the lower left corner.
Yeah,
is typically to represent the angular resolution of the observation. So it's like a beam size.
Okay.
Yeah. Sorry, I maybe should have explained that. But yeah, many of the plots have that.
Yeah. Very good then. All right. Well, let's thank David again for a great talk.